also Professor Williams, you know that. He's a very well-known theoretician. He loves a simple model. So all three masters as simplification. So that's affected me a lot. So let me move to introducing my institute a bit, if you, just in case you're interested. I'm from the Toyohashi Tech. The website is just over that. This university is founded very new, not very new, but it's relatively new. Launched in 1974. I was born in 1971, so it's nearly exactly the same. And our department is very small, but fully devoted to the engineering professionals. And then my lab was located in mechanical engineering, what we call the ECE, which is Energy Conversion Engineering Laboratory. So now I have the 4 professors. I have 3 professional staff, except for myself. And also the 4 research staff as a postdoc. Johnson from the USTC is now helping us a lot. And generally I have the 20 graduate students, but this year I only have 10. I don't know why, but it just happens. And 9 graduate always, then 9 undergrad, and all 9 undergrad will go to the graduate. So we are pretty much good resources for the graduate student. And I have much of the funding from the government and also the fire protection department and a private company as well. And approximately $0.2 million US. You can calculate on that for the Pew Research Fund. This is after overhead. Then these are several the work which I've done in my laboratory, very small scale and not very large scale, just like you did. But because Japan is very small, so I have to make it smaller. This is the reason why I have to work for the scale modeling things. Oops. Well, okay. Then I try to exclude the sounds, but. Oh, sorry about that.
Oh, okay.
Then this is something like I did, what Xiao Yu helped a lot when I was he was in my lab. There is 2 jet flame. It's coming together now. So let me play. Now those flame it just stay. Okay, then it will coming close, and it's try to shaking. And if your eye is very good, the shaking is anti-phase. But once you close more, it stops. Then they close again, it's in the same phase. It has very good repeatability. If your burner is flaming out, then first you have the in phase, then the flame shaking stop. Then it turns to not. Okay, it got me to an antiphase. That's very interesting. But always I show this in a conference. Everybody said that that's very interesting. The next word is how you be interpreted to the engineering. And always I said, I don't know, so you think about it and you give me the answer for that. But this is a kind of pure research science. And Xiao Yu actually published at some physical journal, right? So this was very nice. And I also did a firewall, but it's kind of small scale, within 5 meters tall inch wind tunnels. This is not in my lab, but I borrowed at the BRI, which is the Building Research Institute in Japan. So this is something I had to work on that. So let me move to the space engineering, space fire things. How many you can guess how many accidents which is reported? Okay, non-reported I cannot count. In the space so far, a few were around 10 to 20 to 50, or 50 to 100 were can't count it on. Few. Number 2, around 10.
3.
20 to 50.
The third.
Third.
20 to 50.
20 to 50. How about the 50 to 100? Come I cannot count it. Oh, that's good. I can't count it, so I have no idea. But the reason that the results is 13 cases. That's much smaller. Maybe you could sense. I referred this from the Grundes, Guillaume's group, or Jose's group. But I don't know if this is real or not, but this is reported, or 13th. Then the next one is, I masked over here, the smoke or flame. So there is the smoke fire detection, or the flame fires, but those. Which one should be pay more attention? Can you guess out of the 13th, how many for the flaming, how many for the non-flaming?
Very few for the flaming.
For flaming.
Why?
I
just guessed
that's
that.
Very good guess. And let's say, are you agree with the answer or you are opposed? I shouldn't ask him this way. But you're pretty right. Most likely, the flaming is very small. The 4 out of the 13th. So mostly, they are suffering for the smoke. So if you're working on the space fire research, if you want to do working on non-flaming combustion in low gravity condition, that is the best, because this is a very real story. But most likely, most of the fire, microgravity or fire space engineering or some researches, they always have the flame. But that is very rare case. So maybe flame spreading, well, it may occur, but once flame spreading, it's already too late to extinguish. So you have to work with the smoldering. However, what kind of the flame structure and what kind of potential hazard if you have the flame in the microgravity, this is still very important. So knowledge about the flammability in space is still really needed still. Well, this is the reason why there's many of the microgravity researches, and there is a merit, of course, using the microgravity as relieved. Of course, that's a simplifying. So again, the Saito, Takeno, Foreman love the simplification, so they like the microgravity anyway. So three-dimensional phenomena can be maybe reducing the 2D or 1D and steady state conditions. So it's very simplified, so it's very matching with the theory, but it's good. High order symmetry, or you can possibly touch with the mask, which is very weak condition, which cannot be found on the Earth. So the flow effect can be very carefully studied, or under these kind of conditions, diffusion is dominant processes. That's very different from what we found on the Earth. So by using that, these are the several the examples. There is cellulosic seed, and you ignite it on the top, on the center, and you have the incoming flow like this, and a flame shaping something like that, and the flame is actually moving against the flow. So that's the flame spreading over the cellulose and the microgravity conditions. But it's still three-dimensional. So if you're igniting not on the spot, but on the line, then mostly perfect two-dimensional phenomena can be found. And this is actually NASA's experiment. If you look at the side, there is a seed, like cellulosic seed, and there is incoming flow. Looks like a very good symmetry shape of the flame is spreading like this. So this is a two-dimensional. So if you can go to the two-dimensional, then it's much easier to do the numerical simulations. So these are the numerical simulations working with the two-dimensional constellation. But those are matching with the experiment very well. So which means that you can extract most of the physics from the numerical simulation results. That sounds very nice. Okay, this is a very typical reason using the microgravity to open for the fire science or the microgravity science. But there is a demerit too, which is not reported very well. Once using the parabolic flight or a drop tower shaft, when these are what space stations, those are the technique to having the microgravity involvement. But these are, of course, a limited time, and the gravity quality might be not very good. For if the parabolic flight, probably have the G jitter like 0.01 G or something like this. And drop the shaft, it's much better, but the time is very limited, maybe some seconds or something like that. The parabolic flight, maybe 10 seconds, maybe 20 seconds or something in that range. But if you want a longer microgravity, you have to go to the space. But going to that, very expensive. Maybe Nyan can afford that, but I can't. So I have to think about it the other way around. Okay? Maybe Xiaoyu may handle with that. Maybe some of you might do, but I can't. So, of course, there are limited n numbers. You can't do repeating many times. Or let's say I'm having this material repeating 20 times in the space environment. Everybody said about, oh, that's ridiculous. Why you have to repeat it 20 times? The repeatability is very hard to be checked. The most severe condition is, well, of course, expensive is very severe, but if Nyan do that, then no problem. Okay? Then you can extract this time limitation issues. However, something you cannot avoid is volume limited. You can't burning like this one in a microgravity. It's impossible. If you have the accident, then you're not intentionally you can burn the test, but you always fighting with some volume. This is the done when I was at the NIST, and this is a specialty program, which is what we call the SDS-75. The project name is RITSI. And again, this is a cellulosic seat, and you ignite at the spot on the top, and at the center, then you have the windmill like this, and the flame is, again, moving against the flow. It really looks big if you enlarge, but you can identify that this is 1 centimeter. Then this is burning in the league. What kind of size of the league is just like that? It's something like duct form. Okay? Then these are the duct, and this is the fan to sucking the flow. So flow is from here to go with there, then over the cellulosic seat. And the size of this chamber is 171 millimeter, 85, 95. So this much. Okay. Then you can imagine that this much, and then you put some burning material inside, then it burns. Then you may immediately notice wall effect might be very much affecting on the phenomenon. That might be very too small. So NASA, this was actually NASA's experiment, and NASA was also wondering on that. Then asked the NIST to checking about what constraining effect, what size effect. Okay, but I can't do that in an experiment, so I have to do the numerical simulation. This is what we did when I was in the NIST. Just making a duct form, then compare the simulation with totally open case or confined case. And these are the results from the top view on only the half. The top and the bottom, you have two different cases, but one is the open, which is no wall condition. The other one is with wall condition. Can you guess which one is which? I don't have any reward today, so you don't get anything. So even you get a right answer, but just think about it, right? Open case for the top or the bottom? The top, bottom. Okay, you will guess. The confined case is at the top, and the open case is at the bottom. Well, you didn't get it. Well, the reason is very simple. Well, the first I looked at these results, I thought I did something wrong because once you have the wall, heat might be lost. So maybe flame can be shrink. That was I thought, but it's totally opposite. Once you confine, which is you have the wall, then flame gets bigger, and if the case is totally open, then flame getting smaller. I couldn't get the results, but of course I can analyze because I have the old data with numerical simulations. Then immediately I can understand the reason why is because the flow can be diverged. Once the flame is there, flow is something like a blocked by the flame. So flow is diverging. But if you have the confined case, flow cannot diverge entirely. So flow has to be confined. So the reason why then flow is accelerating like this way. Once you accelerate, much more oxygen can convey over this one. So this H is much more richer oxygen concentration, because the diffusion is the dominant process in the microgravity. But the oxygen can supplied by the flow. So flow effect is more pronounced. So that's the reason why you can get more oxygen, then the flame can be more extent. So this is something like that, the results. So then I bring to the NASA, well, okay, the volume effect is too much. So you have to build bigger one. But NASA said, okay, I can't do that. Then I said, well, that's impossible. Then we got a very fight. Then eventually they make I can build bigger one. But I calculate the bigger one. Now still not. But I couldn't say anything about that because I don't fight any longer with NASA. But anyway, there is the very large effect of a confined case. So I did the simulation with the line ignition case, not the spot ignition. Then line ignition, as I mentioned before, it has to be two-dimensional. So let's have the same configuration. Then you have the line ignition. Then if the flame is totally two-dimensional, then always assumption of the two-dimensional, reducing the dimension, it can work. But eventually, what I found is the flame has a bulge. So the edge is more intense as the exact same, the reason I already explained. So flow is actually accelerating, and much of the action that can be coming over there, then this edge is more intense. So flame is always, the edge goes first, and that center is going to the rest. So I thought that we believe that microgravity can reduce the dimension to more close to the ideal condition. But in the reality, due to by the constraint of the volume, it's not. So we have to notice on that, but not very much people will notice on that. Okay, so if you do the microgravity test, please think about this. And these are the line ignition results as time goes by, and that bulge is actually developing. So as time goes by, three-dimensionality is more pronounced. But in the early stage, it's more close to the two-dimensional. So only limited time, you can probably apply for the two-dimensional assumption, but a longer time, maybe not. Okay, so there is no steady state because this bulge is always developing in time. So three-dimensionality is more pronounced, and this dimensionality might not be no longer available. Of course, there's other cases like polymer sphere combustion in a microgravity. This was done at the NIST 2000. Then looks like very spherical, and you can apply for the one-dimensional droplet combustion theory like this. So obviously, such kind of D2 low might be hold. So this is actually the NIST was actually doing. Well, it's kind of bursting, and then there's only several pictures at the limited condition. So I have to wonder whether this is really one-dimensional can hold and very steady or not. So recently I did a microgravity test by using the drop-top shaft, which is installed at Hokkaido. Maybe you can have the similar, you have the similar thing in Beijing, I believe. And these are the working the bench, and those are students, and this is inside inside the capsule. This is a kind of a rack, this is the kind of combustion chamber. Then these are the specifications, and these are the controlling the devices which is installed in somewhere else like this. Okay, then this is the movie's results, and then once ignited, the flame is fluctuates a lot. So it's really far from one-dimensional steady state. But if you just cut the pictures, you can nicely say that, well, yes, we have spherical, nice one-dimensional plane. Well, I'm not saying that this is cheating, but you must see the fact. Okay, then we're thinking about this is whether applicable of lower dimensionality or not. So what I learned from most of the microgravity research from my career, and the effect of the limited volume is extremely severe, and also sometimes it's not very steady state. So non-steady, maybe three-dimensional features are naturally appeared. So the microgravity might not be always ideal case. So we must, suppose if we need to exclude the microgravity condition, but we'll still want to have the ideal conditions. What else we have? And this is the things I have to think. Then the answer is we must have alternative technologies or methodology to mimic low gravity flame, which close to one-dimensional or less dimensionality. Then I'm moving to them using the scale model to working with this. Then because you apply for the scale model, then you can mimic the same phenomena in a different environment or the different size. So I'm trying to working with everything is in my lab. So small scale and not very expensive stuff to working with the microgravity, to mimic or to simulate the microgravity flames. So let me explain about the scale model. Maybe you already know that, but just repeating. There is a similarity. There is two types of similarity, what we call the similar, and one is static, and another one is dynamic. The static similarity is, for example, this is a car. Shall we use a car? Oh, Nayan's car. Okay. This is my car, right? This is a what we call prototype and the scale model. And it looks very similar, but it moves might be very not very similar. Suppose that, okay, suppose shall you drive this, okay, and I hit the wall and see what happens, then of course the car is crashed. However, if you bring this, my car, put into the wall, it's bouncing back. It's not crash, because once crash, you have to buy another one. So the toy has to be very, very stiff. Right? So it looks very similar, but behaves very different. So this is what we call the static similarity is hold. However, dynamic similarity is not hold. All right, so if you want to mimic or reproduce exactly, which means that you have to fulfill both similarity, which is the static similar and also the dynamic similar too. This is another way to explain about what is the static and dynamic similarity. Again, the static similarity, the shape is similar. So something is very characterized for the shape is, for example, in a triangle, is the length of each line. Okay? We call this is the ABC. And this is the prototype, which is the real one, and this is a small scale model one. That everything was called with a dash. Then A over A dash, or B over B dash, or C over C, that has to be the same. This is what we call the scale factor. Then the similarity, one we call the dynamic similarity, the same kind of definition we can call. What is the characterized of the dynamic? Okay, back to the static similarity, what is the characterized of the shape is kind of the line, the length, okay? But in the case of a dynamic similarity, what is the characteristics of the dynamics is the motion or the power, okay? It's a force. Force is actually the source of the motion. So, for example, in this prototype, force Fa or Fb was subject to this guy, and this is the scale model. The shape is different, but the force is Fa or Fb.
in a case of the FA over FA dash, FV over FV dash, if these are equal, this is what we call the scale factor. This is the kind of dynamic similarity. Okay. Then once you play with this formula, you can work with FA over FV equal to FA dash over FV dash, which is, this is the all quantities given by the prototype, and this is the all quantity given by the scale model. And this is what we call the pi number, like a Reynolds number, a Frown number, or any kind of the pi number. This is what we call like this. Okay, so this is also, you can work in the pi number A over B equal to the A dash over the B dash. So this is also the static similarities pi numbers like this. So holding both similarities, which is the one static and the dynamics, is a key to mimic the targeted processes. Okay. So let me back to the original problem I working with the with the NASA's project, which is the frame spreading out over the cellulose like this. Then I modeled like this. Okay, this is the paper, and this is the flame, and you have the very weak wind, like a 2.0 centimeter sec. So this is the kind of inertia coming over here. Then even though this is a microgravity test, but the gravity cannot be zero, so you might have some residual gravity, even small. So we have the buoyancy. Then because the flow speed is very low, so you must have a very thick bundle layers. So you must have the viscous force. So you have the viscous force, inertia force, buoyancy force. Those three forces is actually working on this flame. So the flame behavior has to be controlled either by these three forces. And then inertia is driven by the wind, very slow wind. So the inertia is very small in terms of that speed. And the buoyancy is also very small, and viscosity is small. So all three forces are equivalently very small, but if you taking the force ratio, which is what we call the pi number, it can be not be negligible. Okay, let me go how to find the pi number. The inertia Fy, buoyancy Fv, viscous F nu or Fv, can be written using a characteristic length or characteristic velocity or those kind of characteristic quantities using like this. Inertia will be expressed by ma, which is the mass and acceleration, and can be interpreted to low length scale square and b velocity square. You can calculate the unit, then it will be matched. Okay, this is what we call the inertia representative the expression. And this is the buoyancy is delta mg, because once you light, you get a buoyancy. So that's the delta m. Then it will convert it to the delta rho L square. L is a length scale, and G is a gravity acceleration. The viscous force is nu Lv. The nu is the viscosity, and viscous coefficient. L is the scale scale, and V is the velocity. Then just taking the force ratio, you can find the pi number. So you have the three forces, so you can actually, theoretically, you can get the two ratios. This is the pi number. Let's say one pi number is the ratio of Fy and F nu, 1, 2, 3, like this. Then getting like that, and eventually it becomes something like this. You may know this. This is the kind of Reynolds number. Right? And the pi 2 is Fb over F nu. Let's say this is another pi number we can define, and this is delta rho L cubic energy over nu Lb. This is not very famous pi number. But there is a velocity, so let's eliminate the velocity to do that. Multiply pi 1 and pi 2, you can extract the velocity, so you can define another pi number. But a pi number is independent variables, so even you can calculate, even you can multiply, then you can establish another pi number, but that another pi number is one of the independent variables. So let's preserve the pi 1 and define pi 3 as the multiple of the pi 1 and pi 2, and becomes something like this. This is what we call the Grashof numbers. So we have the Reynolds number and the Grashof number, two pi numbers based on these three forces. Okay, so then again, the pi 1, the Reynolds number is given by the load, which is the density, L is the length, and V is the velocity, and a nu. And the pi 3 eliminate the V, so it's remain the load, which is the density. Delta low is the density difference, and L is L cubic is the length scale cubic, and G is the gravity factors. And suppose that this is the actual real scale. So I want to simulate this in my lab. So what to do is, because in real scale you have the very low flow, so the Reynolds number has to be small. Okay, then a real scale, the other one is low gravity case. So there is low gravity. So pi 3 is also very small. So microgravity phenomena, you can interpret it in this one as a low Reynolds number and a low Grashof number phenomena. So what we do is, of course, if you're reducing the gravity, you can achieve the small Grashof number. But let me working in a different way by using an equation state, then converting the load to the P. Density go to the pressures. Then this one becomes like this dependency, which is that pi 1 is pressure or pressure 1 and L1. So only linearly correlated with the pressure and also the scale. That's the pi 1. Now what the pi 3 with the Grashof number is a pressure square and the length scale cubic and the gravity acceleration. Again, my target is lower pi 1, lower pi 3 under normal gravity. How we do is, if you have the microgravity, naturally pi 3 is small. But suppose if you have the normal gravity, but you want to have a small pi 3, how do you do? Just reducing the pressure and also the size. And even preserve the gravity as a unity, you can reduce pi 1 and pi 3 as well. So this is actually the key, small scale and low pressure. You combine that, even at 1G, you should have similar microgravity phenomena. Then I try using a low pressure test chamber of the wire combustion. The reason is wire was there when I was in Hokkaido. Then pressure chamber was there when I was in Hokkaido. So I don't need to pay a lot of the facilities, but that's very easy to be done. Then this is a kind of immediate results. If you reduce the pressure, the flame is getting spherical. So it's more close to the microgravity phenomena, as you can see that directly. Then I do the polymer combustion as well. And this is the movie under the, not microgravity, but low pressure conditions. As you see that the flame is totally spherical and you don't have any kind of soot. So those no soot, so there is no soot bursting, but you have the spherical and very steady, so you can have very much ideal condition. Let me briefly explain about what we do over here. This is the test chamber, and we have the spherical specimen holding by SiC fibers, and these are the uniter to ignite this material. Then again, this is the results. You can achieve very spherical and blue flame, and the blue flame is because you're reducing pressure, so you don't have any chance to grow to the soot. Then of course I can check the D2 low is preserved or not. So time versus diameter square of the specimen. If this can fit to the theory, D2 has to be linearly goes down as the time goes by. Again, if you go to the 20 kilopascal, which is the spherical flame, as you saw, it's very clear and nice linear curve. We can find that. So this gradient, this is what we call burning rate constant. Then that number can be compared with the microgravity test, whether this low pressure test works or not. Then this is actually the results burning rate constant K of the microgravity test, which done by the NIST, under the 20% of the oxidizer or 30% of oxidizer conditions. The test results of the microgravity was 1.6 to 1.8 millimeter square per sec. Then 100 kilopascal, which is normal pressure conditions, what you do, the burning rate constant K, which is the gradient of the D2 versus time, is 2.15 or 2.07. It's much higher than what we found in microgravity. But once you go to the reducing pressure like this, and becoming the very spherical flame like that, which is a 20 kilopascal, the K value is very close to what we found in microgravity. But this microgravity test is, the N number is only 3. So there's much of the variation. So I'm still not very much concerned about the really this is equivalent or not. But as you saw that once you have the spherical flame, most likely the phenomena can be reproduced. Then this actually telling that a shape is very important to decide the burning rate constant. So burning rate is actually governed by the flame shape. So once you have the perfect flame shape, which is the very steady and very even less luminous, you may have the very close results like this. Okay, because I have running out of time, so I don't have so much. Should I? Okay. Well, then these.
Want to play the video?
Oh no, I think I have to stop, or I still have the slide. Okay. Oh no, that's fine. Okay. So let me a bit move to the large fire experiment. If you want to do a scale model test to reproducing the large scale fire in a space, let's say fire on the Mars or fire on the moon, what do you want to do? Of course, you can't do the test. If you can do the test, there is no reason you need to work with that. So you have to find some alternative way to mimic something in fires and what can happen in the Mars, and then you have to predict what kind of damage could be happens. So let's think about the same pi number things. This was actually applied for the small scale fires. But the same for the inertial buoyancy viscous can be applied for the large fire too. For the large fire, because the size is large, so you're naturally concerned about the Reynolds number has to be very large. The Reynolds number, which was pi 1, was the ratio of the inertia versus viscous force. So if you want to have the large Reynolds number, you're reducing a viscous, then you can achieve very easily to high Reynolds number anyway. And if you take the another ratio of the inertia versus buoyancy, that what we actually found that's the flood number. The flood number becomes like this. So the velocity square, length unit, and unity, and gravity -1. So in a real scale, like in the Mars or the Moon, the pressure is reduced. So this pi 4, and also the size is high. So your pi 4 is kind of big. So current case, Reynolds number is very high, and the flow number is sufficiently large. Then you have to reproduce this phenomenon under the normal gravity
with some pairing with other kind of factors. How to do that is how to, well, let's say how to get the higher pi 4 in large scale. Well, that's very easy to have the large scale and a low gravity, then you have very large number of the pi 4. But if I want to simulate this in my scale at my lab is small, so L has to be very small. Okay, and then gravity has to be high as compared to the space. So to equivalent, I have to increase the velocity. But increase the velocity is nearly inertia dominant phenomena. That's not the buoyancy controlled phenomena. So it looks likely it's not really right. But I want to enlarge pi 4. Otherwise, I cannot reproduce the real phenomena like this. Then how to do that is, I was eliminate the low phenomena before, but just preserve this low. Then suppose your low, which is your density, is very higher, then naturally you can get a higher Reynolds number, and also you have the higher Reynolds number. So which means that in the fire case, you're working on with the density of the air. But if you can increase your density of your test device, you can get a very easily high Reynolds number and also the high flood number, even though your scale is not very large. So this is the reason why saltwater water model is working very well. You know the saltwater water model like this, that in inverse, and you have the salt, you're actually dripping down, but if you see the inverse, it's more likely flume is developed like this. So this is actually the reason why the saltwater water model works, and because saltwater water model becomes something like that. This is the fire case, this is the saltwater water case. What you need to preserve is your theta's the prime or the star has to be equivalent for the fire case and the saltwater water case, and including the gravity terms over here. So in the real fire case, you can get that, right? And my model and the saltwater water, you can control this. But my gravity is normal gravity. But I have another quantities to change to get the same phenomena which happen in low gravity in the real fire case. The result is I can control the density difference. So if I can control the density difference, which is a low minus low rho naught, then I can compensate of the difference of the gravity by manually like this. So low minus multiplied G2 has to be equal to T minus T naught multiplied by the G1. So if the G1 is lower and the temperature difference is some sufficient temperature differences, but I can changing the low the density difference of the ambient water and the saltwater water, then I can mimic similar or the same number of like this. Then I can preserve the same theta star as the modeling factors. Then it's very easy to calculate if you get a 1G, which is the equivalent to 20% of the solvent of the saltwater water. But if you want to model 1/3 of the gravity, you can very easily calculate 6% of saltwater water can resist to mimic 1/3 of the gravity plume evolution phenomenon. Then this is the results. Of course, this is the inverse movies of 20% of saltwater water, which is 1G fire simulators. And this is 6% saltwater water model, which is 1/3 G simulators. So this must be Mars, and this must be on the Earth. So there's a big difference, of course, in plume rise, and again smaller, and then Then once it hitting to the ceiling, then the evolution of the plume and also the plume thickness is, of course, very much different as compared to that. So these are the kind of a model which is happening on the Mars, and then you can imagine what kind of the detector has to be placed on somewhere else, and how to fighting with the smoke if some fire case happens on the Mars. I presented this one to the JAXA on the other day, and the JAXA say, the audience immediately saying, well, the question, how you can prove? They can't prove it. So I have to answer to the JAXA, you go first to go to Mars, then prove this. Then they said, you have to prove, but I can't do that. Then it's kind of a big fight. But saltwater water model, I believe, can work for the low gravity case, at least the plume evolution phenomenon. And also maybe if you think about the evacuation, you can of course consider about this kind of modeling. Okay, so I'm sorry about I have to skip several, but this is actually the remarks. Scale modeling concept works to mimic the phenomena under extreme condition like microgravity. And if the proper scaling law is successfully found, you have to adapt somehow, like changing the density, or changing the scale, or changing the pressure. But you have some way to do that. But if you can't do this, then you cannot do the scale model test anyway. But if you can find some proper scaling law, then you can do that. So yeah, think about it, whether the possibilities. And just remember that no single method can tell all. So you have to work with, it's better to work with a multiple methodology or approaches to recommend it for studying the fundamental physics, also background physics as well. And I'm launched a new book, well, no, not a book, it's a journal, only focusing a scale model, which was actually initiated by the Saito, and now I'm taking over as the editor-in-chief. Progress in Scale Modeling, an international journal, and this is the URL if you want to submit some paper only focusing on scale model. I'm happy to receive those kind of work. I'm sorry for their taking a lot of time, and thank you very much for your kind attention. Thanks.
Okay, thank you, Yuji, for a very, very good talk. So it's time for asking questions. So if you have, please ask questions. Okay. Very good talk. So using the scaling modeling, so we can do many things. So first, I have one question. You know that, so in all aspects of the fire research, we use the scaling modeling methods. But sometimes you know that, especially for very large scale phenomena or some involving very complicated chemical reactions. So we especially in very special environment, we face many kinds of scaling numbers. So we have to give up some of them. So
yes.
It's very complicated. Sometimes we are on the wrong way for the final solution.
Yes.
So this is a very small scale, and also, but it's very complicated. So if for the very large scale fire research, so what's about your consideration about for the future research?
Okay. Well, thank you very much. It's getting very nice point. I mean, if we want to preserve, for example, the dynamics and also the chemical reaction at the same time, because those are very different time scale. So if you want to do the same scale model at the same time, mostly it doesn't work. So as Nayan mentioned, you have to give up something. But in the other way around, you're giving up this, the simulate the exact same phenomena at one time. You're giving up, but you divide it on this aspect. You do this scale model, but that one is in a different design to work for only for the chemical, and this is only for the dynamics. Then you combine the results. I think this is the only way to do that. Or you directly go to the numerical simulations if your numerical model is sufficiently confident. This is something always be on the discussion. But recently, the numerical power is very good. So you can go to the numerical simulation for the different scale. But like, you know, for the spire size, that's still not possible to do the direct numerical simulation. So I still believe some scale model test is available, and just splitting for the objectives. This is actually you do the necessary thing to do that. So
Yes.
I can't have any good answer for this, but always work with the very different time scale, then we have to divide. Then this is the only things I do, and it will successfully work, I think, as far as I did. So.
Yes. So, another question, please? Please. 小雨，你这个没有装电池是吗？哦，OK。
So I have an open question. So what we have discussed talk about today is all about the physical part. You know, for file we both involve physical and chemical part. So for scale modeling, we know that sometimes in some cases it really works. So my question is, under what condition we have to consider about the chemical effect? For example, when we want to simulate the reduced gravity, under some cases maybe the chemical will be important, then we have to consider some things.
Right. You're right. And for example, the burning rate and also the ignition, if you want to simulate the both. The ignition is chemically controlled, but the flame spread or burning is dynamics or physical mass and heat transfer is controlled. So those two controlling factors different. Then of course you can't match at the same time, same one series of the test. So if you go to chemical dominant phenomena, which is your time scale must be very, very small, then you have to design a scale model which control the time scale is emerging. So maybe the burning material is different. One replace the different chemical agent to make the reaction takes longer time or something like that. So this is kind of one of the way to do the scale model.
So can we also develop some scale modeling numbers involving both physical and
Yes.
chemical power, for example?
Yes.
Ampere number or something like that?
Yes.
Okay.
Possible.
Okay.
but don't tell me what. Okay. But technically possible, because the Duncan number is actually the control number of the chemical time and the dynamic time. You can control dynamic time, but you can also control the chemical time as well. So you can change the chemical reaction to control the Duncan numbers.
Okay, I hope the students can ask questions, especially the students who have the direction of the flaming combustion. So I can just can ask Yan Yuhui. You should ask a question if you have. Okay, so some students are very shy.
Okay.
Especially He Zhuoyang. You understand the lecture?
Yes, I understand the lecture.
Okay, please.
Well, I have a question because my experiments is about the topography, the terrain, and the wind. So you are in your research, you are mainly focused on, I think you are mainly focused on the small scale. So in that such large scale, with wind and with different complex terrain, how can I use the scale model?
Okay.
So this is a question because I'm thinking in the experiment, in the research, you can only do some small scale for fair research, for welfare research, but in the reality, the fair is very large. So I don't know if I feels how to model this, how to use the scale model.
Okay. Well, actually, working with a large scale is much easier. For example, the forest fire simulating with on the table is very difficult. But as forest fire will simulating on this room size, this is also scale model, right? You have to reduce in scale, but not reducing this size. Right? Working in a small scale, always you have to fighting with a large Reynolds number. You have to adapt. You have to apply for that. So there is some scaling though, depending on what kind of size you're interested in. But always, you don't need to considering about the manipulate with the viscosity if you're working with some certain size of the phenomenon. So there is scaling law, of course, but you don't need to working with very difficult scaling law, which will be happening in a very small scale.
Yes. So your means that maybe I can focus on the scale modeling on the boundary condition. I can neglect or ignore the scale modeling such as viscosity, the effect of viscosity.
Right. You can neglect, but if your interest phenomena is somehow very near the surface, then maybe you cannot neglect any viscosity effect. So it depends what kind of issues you are looking for. So your phenomena is governing by some very small scale of the in the boundary layer. Then flaming, then your post-flame structure is actually governed by that. Then you have to working on this. But you don't need to work on that, but you want to see the some shape of that, then you don't need to working on those kind of parts. So you have to split the problem, then model different way.
Thank you.
Well, any publication I see, then I see the model, then I can sense what kind of things you want to focusing on. But some work is really mixed, then I always reject. So be careful. Thank you very much.
Okay, any other question? I just think that, for example, in our experience for studying the firewall, you know that when we study very small firewall, it's very easy to, but we need to have the circulation around the flame, and also the circulation field has a very large height, for example, extending until the flame height. But for the firewall in reality, so you know that we need to have very small height of the circulation around the flame to induce the firewall. So it's very sudden change or some change of the mechanism. So involving the interaction of the fluid mechanics and also the combustion.
Right.
So it's very complicated. So we are also studying the appropriate the scaling modeling method for understanding the formation of the firewall.
Right.
So it's very complicated.
Right. I think the boundary condition
boundary
has to be
relation
very
important.
Right. You must ejecting some flow or to mimic the thickness of the boundary layer thickness.
Yeah,
Yes.
especially compared to the normal flame. So you know that the L entrainment enters into the flame mainly from the boundary layer.
Right.
Okay. So if you have other question? So okay. So if you have no questions, you can. So I encourage you to have discussions with Professor Yuji Nakamura. So by other means, for example, after the meeting, so you can discuss with him. So and you can use all the opportunities to have the academic exchange, academic discussions. Okay, let's finally thanks to Professor Yuji Nakamura for his very excellent speech.
Thank you very much. Thank you.
Thank you. So let's close the